Hello and welcome to this further math support program online revision session. This one's on numerical methods and is going to cover numerical integration. So the things that you need to know from the specification: you need to know how to find approximations for integrals using the midpoint rule, the trapezium rule and Simpson's rule. And you have to do that obviously to the accuracy that they want from this. It's useful also to know the relationship between the methods. There's some formulas that you can use to speed up calculation, and in fact you are expected pretty much to use those. So you're expected to know that Simpson's rule is a weighted mean of the midpoint and trapezium rules, and you're expected to know that you can calculate subsequent trapezium rules from a previous midpoint and trapezium rule. So first question we've got here is from January 2010. It's question 2, so it should be fairly straightforward, though there are 7 marks on it. They're not telling you what the integration is, they're actually just giving you values that have been previously calculated for the midpoint and trapezium rule in the table, and they've got that midpoint rule for a gap of 1 and then for gaps of 0.5. And it wants you to work out the next trapezium rule to start off with, and then find some Simpson's rule estimates, and then state what the value of the integral is likely to be. So there's our table, and the first thing is we need to know this shortcut, that you can work out the next trapezium rule estimate using the previous midpoint and trapezium rule. So what we do is we tend to call our first approximations M1 for the midpoint rule and T1, so then it's T2 and then it would be T4, because what you're doing there is doubling the number of trapeziums you're using each stage. So these things go M1, M2, M4, M8, M16, or T1, T2, T4, and so on. So to calculate T2, we just work out the average of M1 and T1, and using their values there, we get that value, which we write to 6 decimal places because that's what the mark scheme is going to be written as, and also they've done that in the values that they've already given you, so there's a clear indication of the accuracy that they want you to write it to. Okay, I've filled it in now in the table, and then it wants us to find 2 Simpson's rule estimates. So just like there's a shortcut to work out the trapezium rule, provided you know the previous midpoint of trapezium, Simpson's rule is a weighted mean of the midpoint and trapezium rule values. So if I want to find out the first Simpson's rule estimate, I do 2m1 plus t1 over 3. That's because the midpoint rule is always twice as close to the real answer as the trapezium rule approximation. So, doing our weighted mean, just putting in the first values for the midpoint and trapezium, so the 2.579768 doubled, plus one set of the 2.447490, added together, divided by 3, gives us that. We can then use the values where h is 0.5 for midpoint trapezium, so that's m2 and t2, to work out s2. So we're going to have to use the value that we calculated before, and so we double the midpoint rule, the 2.547350, add on the 2.513629 for the trapezium rule, and divide by 3, and we get that value. Again, both those written to 6 decimal places because that's what you have to do if you're trying to follow the consistency of, well, you're trying to be consistent with what they have in the table that they've given you. And in fact, the mark scheme will be written with 6 decimal places as well. So, the value of the integral to which that seems to be justified from that is, if you look at both of those, they actually both round to 2.536 to 3 decimal places. So I've just written that down. I haven't given a reason yet, but just looking at those two values, it looks like they're both round to 2.536. So I have to put that in words. Basically, the Simpson's rule estimates both round to it. And the thing is, the next estimate, if you went on and calculated S4, and this is probably going a little bit too far for the marks that they award for it, but if you go on to calculate S4, the ratio of the differences is, for Simpson's rule, for a well-behaved function is 0.0625. So basically that means the next difference would be a 16th of the current difference, so the next gap would be a 16th. Now, those are our two estimates. Our current difference is 0.00435. If I work out a 16th of that, the value there we've got is 0.00002787. At best, that's going to affect the fourth decimal place. So writing out an answer to 3 decimal places is going to be fine, because any further value is only going to have the 4th decimal place affected. So let's look at the mark scheme for that. For calculating our first trapezium rule estimate using that formula, that shortcut, you get 1 for the method and then 1 obviously for the answer. For calculating the Simpson's rule estimates, you get 1 for the method of knowing that it's that weighted mean, twice M1 plus T1 over 3. We've used that formula basically twice. So you only get 1 method mark for that, but you get 1 mark for each of the answers. You get 1 mark for selecting an appropriate accuracy for your integral, and 1 mark for your explanation. My explanation goes far too far. It's really a case of the Simpson's rule estimates. We got both round to it, and the fact that S4 won't be different by that much, because the ratio of differences is 1/16. Okay. Next question. This one's a much harder question, much longer. It's question 6. It's got an 8 mark, a 7 mark, and a 2 mark bit to it. So there's going to be a fair amount of effort required to answer it. This time you are given what the integral is that you're calculating, and you're given the midpoint rule estimates for the midpoint rule and the trapezium rule estimates for h equals 0.8, so you're given 2 values to start off with. It then asks you to find the midpoint and trapezium rule estimates if we then go to the next stage, which is h equals 0.4 and then h equals 0.2. And then from that find 3 Simpson's rule estimates. We'll come back to the rest of the question in a second. We'll do that bit first. Okay, so we've got to find the midpoint rule estimate with h equals 0.4. Now the way the midpoint rule estimate works is you're splitting it up into rectangles, and if h equals 0.4, what we're doing is we're splitting it up into 2 rectangles. Now I know that because the gap between the limits on my integral are, well, it's 1 and 1.8, so the gap is 0.8. And if I've got h equals 0.4, that goes into that twice, so I'm going to have 2 rectangles. Now, you have to work it out. Obviously the rectangle starts at 1, the first rectangle starts at 1, and then it finishes at 0.4. You have to work out the height from the midpoint of those 2. So halfway between 1 and 1.4 is 1.2. So what I do is I work out the height of it by subbing in 1.2 into the thing I'm integrating. That's the formula, that's how we work out the y-coordinate. So I work out the height at that point. That's the height of my rectangle. The width of my rectangle is 0.4. But that's going to be consistent for the second one, so I can actually factorise out the 0.4, which is why I've written it at the front. Now the next rectangle is going to start at 1.4 and finish at 1.8, and so the midpoint of those is 1.6, so we calculate our height from 1.6. So I'm actually having to calculate using the midpoint rule formula properly. There's no shortcuts for this, and so I have my 2 midpoints, work out the y-coordinates, and then times it by 0.4, which is h in this case. And when I do that, I get that to the 6 decimal places that we tend to use. Okay, again, I'm being consistent because they've given us the estimates to 6 decimal places. It's making it very, very clear that that's what they want their answers written to. So we do the same for h equals 0.2. And for h equals 0.2, we're going to have 4 rectangles because we're going to go from 1 to 1.2, 1.2 to 1.4, 1.4 to 1.6, and so on. Now, we have to think about where those midpoints are. From 1 to 1.2, halfway is 1.1. From 1.2 to 1.4, halfway is 1.3. From 1.4 to 1.6, there's halfway, and 1.6 to 1.8, there's halfway. And so they're the values that we calculate our heights from. And the width of each of the rectangles is going to be equal to h, which is 0.2. And so we calculate it, and we get that to our 6 decimal places. So what we've done is we've found the midpoint rule estimates for h equals 0.4 and h equals 0.2, we now need to find the trapezium rule estimates. So what we do is we use that trick that we did before, that T2 is the previous midpoint plus the previous trapezium averaged. So M1 plus T1 over 2. So there's M1 and T1 going in there over 2, and I've got T2. Okay, for h equals 0.2, T4 is going to be M2 plus T2. In fact, I've actually written T2 first there, but it's M2 plus T2 divided by 2, and we calculate that, and so we've got our T4 estimate, which is where h equals 0.2. So we've got both our estimates for the trapezium rule. So from that we have to find three Simpson's rule estimates, and we use that weighted mean formula, 2m plus t over 3. So S1 is 2m1 plus t1 over 3, and we substitute the values, and that's what we get out. S2 is 2m2 plus t2 over 3, and again we substitute the values, and that's what we get out. And S4 is 2m4 plus t4 over 3, and again we get those values out. So there's our three estimates of the integral using Simpson's rule. So we've got to give a value for I that appears to be justified from those three Simpson's rule estimates. So looking at all of those, it's looking like as we go down that list we're getting 1.5689, and then we've got, for S2 we've got 5.3, and for S4 we've got 4.9. They both round to 1.569895 to 5 decimal places. They both round to the same thing, to 5 decimal places. That appears to be justified, but we need to think a little bit more about this. It's to do with the differences and how much that's going to affect the figures. So they've currently got a difference for S2 and S4 of negative 0.000, well, you can count the zeros, 4. Okay, that's what they've got as their difference, and it's negative because it's decreasing. Okay, S4 is lower than S2. Now the next difference would be a 16th of that, which is going to be negligible in affecting that fifth decimal place. It's not going to affect that fifth decimal place because a 16th of that negative 0.0000004 is not going to affect the fifth decimal place. So from that thing we can actually say that we're fairly confident that it's that to 5 decimal places. Okay, now what we're going to do is take that answer to be exact, and they want us to put a table of errors for the midpoint and trapezium rule estimates of I. So there's our table, and we're going to write down the midpoint error and the trapezium rule error for the different values of h that we've got. So there's the three different values of h that we've used. And what I do is I do the approximation minus the accurate. So in other words, I'm going to do the approximation, each of these estimates, and I'm going to subtract the value from part 2 that we're saying is exact. So that means that if the approximation is too high, we'll get a positive value. If the approximation is too low, we get a negative value. So we have those values, and we just do the approximation subtract the accurate, and in this case the midpoint's below each time and the trapezium rule is above each time. Okay, and we can't go better than 5 decimal places because we're using our exact value as 5 decimal places. So we've used the 3 approximations for the midpoint and 3 approximations for the trapezium, and we've done approximation take away what we're considering to be exact. So the next stage asks us to explain what those errors show about, first off, the accuracy of the midpoint and the trapezium rule. So let's think about what that A statement says, the relative accuracy of the midpoint and trapezium rule. Look at the errors in the midpoint rule and compare them to the trapezium rule for the same stage. For the midpoint rule, the error there is about 0.02, and the trapezium rule is about 0.4. Here it's about 0.005, and here it's about 0.01, and there it's about 0.001 and 0.002. The trapezium rule error each time looks like it's twice the size of the midpoint rule. Okay, so basically you say either the trapezium appears to be twice the midpoint, or the midpoint, in this case I've written down half of the t-values, so the midpoint rule approximations are twice as accurate as the trapezium rule. Now there aren't many marks for this. The other thing that you could say is that they're always one side of different sides of the actual answer, so the midpoint is always, in this case, the midpoint's too low and the trapezium's too high, so the midpoint's underestimating, the trapezium's overestimating. But it's actually asked in the question for the relative accuracy, so that would be another statement that you might say if there's a fair number of marks on it and you're trying to make sure you get everything. I've just kept it down to, because it talks about the relative accuracy, I've just kept it down to the size of the two approximations, and it's quite clear there that the midpoint is roughly half of the trapezium. Okay, for B, it wants the rates of convergence of the midpoint and the trapezium rule. So you need to think about the rates of convergence, and that means that you consider the error as you go from one stage to the next each time. So if you look at, I've uncovered that a little bit too quickly, but if you look at the midpoint going from one to the other, it's roughly being divided by 4. Now you should really use a little bit of prior knowledge. You should know that this happens with both the midpoint and the trapezium rules. It's easy to spot, I suppose, with these two values here, that it's being divided by 4. It's sort of okay to spot it with those two values there. But it helps if you know that before you start, and that's going to happen for well-behaved functions every time. So here, the errors are roughly divided by 4 for each halving of h, and if that's the case, the rate of convergence is the same for both, and you probably need to get all the marks on this to say what order of method you've got. Okay, now be very careful here, because order of method is different from order of convergence, but I've been very lazy here and I've just said they're both second order. They're both second order methods. So I've just left it at that statement. And having looked at the mark scheme, that's fine for the marks. Okay, so let's look at the marks for these. So for working out your midpoint values, you get 1 for the method, because you're basically using the same method twice, and 1 for each answer. Same for the trapezium rule, that you get 1 mark for the method, but you only get 1 mark for doing both answers. For Simpson's rule, same thing. You only get 1 mark for the method and 1 mark for the overall answers, so all 3 of those. So just bear that in mind, that you have to keep being very careful with your calculations at each stage. Okay, for writing down a suitable value for the integral, you get 1 mark, and for explaining that, you also get a mark. For part 3, you get 1 mark for using the correct method of calculating your errors. Now, I'll point out that I use the approximation minus what we take to be exact. You can do it the other way round, provided you're consistent throughout. So everything you do works that way around, so every error sort of question you do that on. So provided you're consistent, it's fine. I always do it this way around because it makes it clear whether my approximations are too high or too low. Okay, so you get basically 1 method mark and an answer mark for all of your errors in the midpoint, and an answer mark for all of your errors in the trapezium. So the explanations, you get basically 1 mark for your explanation, and you get an answer mark for relating that to the sort of size that it's going. Okay, so it's basically for saying that it's one of them's half the other, and explaining it, therefore the one approximation is twice as accurate as the other. For this one, you're going to get a mark for your general explanation as before. You're going to get an answer mark for saying that it's divided by 4, and you're going to get an answer mark for saying it's second order. Remember, that's second order method. Okay, next question is January 2011, question 2, and again, this has got an integral where they haven't, like the very first question we did, it's got an integral where we haven't been told what we're integrating, but we are given some midpoint and trapezium rule starting values. So the first thing it asks us to do is to copy out and fill in that table. once we've done that, some Simpson's rule and then giving a value for the integral. So it's like a part of the question that we did before. It's only worth 8 marks as opposed to 16. So here's our table. We have to fill this in. It says everything that you can calculate. Well, I can calculate the next trapezium rule value because I know the previous midpoint and trapezium. So I add those together and divide by 2. So I look at these first two values here and here, add them, divide by 2, and that gives me, in effect, T2. I then add these two and divide by 2, and I can work out that trapezium rule. What I can't work out is that there. There's no shortcut to working that out. We'd have to have the function, which they haven't told us. Okay. We now need to obtain the Simpson's rule estimates that can be found. So we're going to use that formula again, the weighted mean, and we sub in the values that we had in our table. So we can do 2m1 and t1 and divide by 3. Then we can do s2 because we've got m2 and t2. What we can't do is s4 because we only have t4, we don't have m4. Then it asks us to give the value of the integral to which the accuracy, to the accuracy that appears justified. And again, looking at those, it looks like 1.777 is where it's heading. The difference between those isn't very much, and then in the next one will be a 16th, so it looks like 1.777 seems justified. And so if you think about it, the difference is only about 0.001 between the two of them. The next difference would be even smaller. So I've not done that much explanation on there. It would be a 16th of the size, and that wouldn't affect the third decimal place. Okay, so the marking for that, 1 mark for the correct method and 1 mark for each of the two answers. Look what it says on the mark scheme as well. It says that you'd lose 1 for any additional answers. Don't worry about the extrapolation. I'm actually going to do a question with extrapolation in later. But it would be a bit of overkill, and it's actually referring not just to the trapezium rule ones here. You'd lose 1 mark if you did any extra Simpson's rule as well. So, the Simpson's rule estimates, we get 1 mark for the method and 1 mark for each answer. And then we get 1 mark for the value that appears justified and 1 mark for our explanation of why that is. You'll notice that explanation has been fairly similar every time I've done these, so you can get sort of used to writing the same sorts of things. Okay, so now we're on to May 2011 and it's question 6, and again another long question. This time it's 18 marks, so there's a lot of marks on it. They tell you the integral, and you've got a gap there of 0.8 to start off with. So the gap between 2 and 2.8 is 0.8. So what they're talking about here is finding the midpoint rule M1 and the trapezium rule T1 estimate of that integral. And so what we're going to do is we'll work those out, and we have to work those out from scratch. We can then use shortcuts to do some of the other bits. So the next thing it asks is from the two estimates find a second trapezium rule, which we can do by shortcut, and Simpson's rule, which we can also do by a shortcut. So let's go through this. We've got to do the midpoint and trapezium rule for 0.8. So basically the midpoint between 2 and 2.8 is 2.4. So we sub that into our y coordinate and we get the square root of 1 plus 2.4 cubed, which we then times by the width of it, which is 0.8. So that's our first midpoint one. Now, one thing to point out is this question, we usually write everything to 6 decimal places. This question states, give your answers to 7 unless instructed otherwise. So I've written it to 7. Okay, now the first trapezium rule estimate, it's best if you actually calculate it as a trapezium rather than trying to do things that are silly with triangles and rectangles. So for the trapezium, you need the y-coordinate of the first point and the y-coordinate of the last point, because they'll be the parallel sides that you've got. And then the gap between those parallel sides is 0.8. And so you use a formula for calculating the area of a trapezium, which is a half of h times the sum of the parallel sides. So there's a half of h. going in there. And the sum of the parallel sides, well, we have to do it from the first point, so we use 1 plus 2 cubed, and then the last point, so 1 plus 2.8 cubed. Okay, calculating that gives us that value to 7 decimal places. We then have to use those two estimates, so we've got them there, to estimate Simpson's rule. Sorry, a second trapezium rule and a Simpson's rule. So the second trapezium rule is using that shortcut, which gives us that value to 7 decimal places. And the Simpson's rule is that weighted mean again, 2m plus t over 3, which gives us that. It then asks us to find a midpoint rule estimate with h equals 0.4 to get a second Simpson's rule. Now, the point is, to be able to work out that second Simpson's rule, we are going to need something we've already calculated. We're going to calculate M2, but we're going to need T2 as well. Now T2 we'd already calculated, so there it is sitting there. But M2, we're now dealing with a width of 0.4, and so we need our first rectangle to go from 2 to 2.4, and the halfway point is 2.2. And then from 2.4 to 2.8, the halfway mark is 2.6. And so we calculate M2, which is the midpoint rule estimate with h equals 0.4. So we use that with T2, using that weighted mean again, to calculate S2. And there it is to 7 decimal places. So it gives us a midpoint rule for the next one, so with h equals 0.2. And then it wants us to find a third Simpson's rule estimate. So we've got M4 there. To work at S4 we need T4. So S4 contains T4, so the first thing to do is calculate T4, which we can do by that shortcut. T4 is M2 plus T2 over 2. We know those values, so we can calculate it. And now we can calculate S4 by doing twice M4 plus T4 divided by 3. And there's the value for that. So we've done the third Simpson's rule estimate, and we now have to show by looking at the ratio of differences that it's of order h to the 4. Okay, so we're looking for it, show that it's fourth order. And it wants us to give the value of I to the accuracy that appears justified once we've done that. So here's our estimate from Simpson's rule. If we calculate the differences, always do the later take away the earlier, so S2 take S1, S4 take S2, and it's going down, so we get these values. And then we work out the ratio of differences. And the ratio of differences is nearly 0.0625, which is a 16th. And that's what you'd expect. It's heading there. You'd probably have to do a few more estimates before it looked really like that. But if it's heading towards 1/16th, 0.0625, you know that it's of fourth order. Okay, so it's a fourth order method. So that shows us that ratio that it's about that. Okay. So we know that. We now need to find what's a sensible value for it. And I decided to show you an extrapolation because we haven't done much extrapolation in these. So one of the ways of doing this is to extrapolate to infinity. What we've on the whole been doing is just looking at our values for s's as we look at the last two, see what they round to the same thing. So they both round to 3.09219. Okay, for example, and then you look at the difference and you say, well, if that's then divided by 16th, it doesn't affect it. I'm going to show you an alternative way of getting the marks, which is extrapolating. So to extrapolate to infinity, you imagine that you just keep dividing the differences by 16 and then keep adding those on. Now adding a negative just means it's going to go down. You keep adding those on to infinity and what you get is an infinite sequence. Now what you do to do that is you use the last calculated value. So we've got that going in. Then you use your last difference. And the point is that's going to then be divided by 16, then we're going to add that divided by 16, then we're going to add that divided by 16. So we can actually take out a factor of that negative 0.0 whatever, and we end up with a geometric sequence with the first term of 1/16 and a common ratio of a 16th. So all we have to do is work out what that adds to, the sum to infinity of a geometric, where we know the common ratio is 1/16. So the common ratio of geometric is is 1/16. The sum to infinity is a over 1 minus r, and our first term is 1/16. 1 minus r is also a 16th, so we get 15/16. And actually for Simpson's rule it's always this, you get basically when you get that it's 1/15. So our extrapolation becomes that, and it shows us the worst that's going to happen roughly to our figures when we keep going. Now, comparing that extrapolation to our s to the 4 means that we can see that as we keep going, those extra figures that we have there aren't affecting the decimal places up to here that we have on S4. So if I'm using S4, we can say that that seems reasonable. So that would get you the marks provided you showed the extrapolation. If you didn't want to do it by extrapolating to infinity, you could have written that it's 3.09219, saying that S2 and S4 both round to that, and because the difference is so small between them, when we divide that by 16 it's not going to affect it. Okay, so let's look at the marks for that. We get 1 mark for our midpoint method and an answer mark, as we do for our trapezium rule. Now I've put up the comment that they've got on the thing that you lose up to 4 answer marks if you've done it to 6, 5, 4 or 3 decimal places. Okay, so for each one you do that, you'd be losing an answer mark. So make sure you read the question. It says 7, so we have to do 7. And that doesn't just apply to these two here, it applies to the next ones as well. So it applies to the second trapezium rule and the Simpson's rule. Okay, 1 method for each of those and 1 answer for each of those. Next one, we get 1 for the method for finding the midpoint and 1 for the answer, and then we only get 1 mark for getting the Simpsons right. Okay, for working out T4 you get 1 mark, for working out S4 you get 1 mark. The reason why you're not getting any more though at this stage is because you're using formulae that you've used before several times. Okay, so for the next bit, when we get up to this showing the ratio of differences, that it's h to the 4, you get 1 mark for the method of showing that all in that table the differences in the ratio. You get 1 mark for the answer of that ratio coming out close to 1/16, and you get 1 for your explanation. Then for the final bit of saying the value that seems reasonable, you get 1 mark for picking a reasonable value, provided it's accompanied by a suitable explanation, and my extrapolation one there is fine. I've actually put the answers in so you can see that they actually did say that it's fine to extrapolate. There you go. That's the alternative one if you had done it by thinking about just S2 and S4. So I've done it by the extrapolation, but you could have done it by the other method provided you've got some explanation in there. And that's the end of this revision session.